Let us now go to our second part of the module Math and Communications. We now discuss cryptography. This is the first part of cryptography. So for this module, we will look at the different ciphers, and then for the second part, we will look at the more modern cryptography, and that would be RSA. So let's think about this. How does mathematics help us in establishing secure communication? So here is our real world problem. So suppose we have a sender, let's call her Alice, and then this is Bob. Alice wants to send a message to Bob, and it's possible that we have here Eve, an eavesdropper who want to read the message that Alice wants to send to Bob. Okay, so we don't want Eve to listen to the conversation or read their message thread. So what Alice would do, so she has a plain text message, and then it has to be encrypted using a key, so that whenever if Eve sees that, she would not be able to understand it. And then Bob, if he will receive this jumbled message, sort of, and then he will use that key to decrypt it so that he would be able to read the plain text or the message that Alice wants to send to him. Let us first discuss the meaning of encryption and decryption. Encryption is a process of using an algorithm to transform information into a format that cannot be read, whereas decryption is the process of using another algorithm to transform that encrypted information back into a readable format. Okay, plain text versus ciphertext. The original information is what you call the plain text, and the encrypted version, the one that you cannot read, is called the ciphertext. What are the objectives of encryption? So number one, we want to have confidentiality. So what that means is that the sender and the receiver can be assured that no third party can read the message. We are assured that no eavesdropper can read the message. Integrity, we can be sure also that no third party can make changes in the message. Remember, for confidentiality, no third party can read, and then for integrity, no third party can change the message. Authenticity, we want to make sure also that the receiver is sure that it was the sender who really sent the message. Non-repudiation, Bob can prove, Bob here is the receiver, to any third party that it was the sender who really sent the message. So meaning to say, he can show it to the banks. For example, oh, Alice sent what's that? This bank transfer. So I am here to claim my money because Alice sent it to me. So something like that. He wants to establish non-repudiation. Okay, let's now talk about some examples of ciphers. So the common ciphers that we have would be the substitution ciphers. They work by replacing each letter of the plain text and sometimes punctuation marks and spaces with another letter. Okay, so that's why it's called substitution. You're just substituting each letter with another letter or probably punctuation mark. So we have two kinds of substitution ciphers. We have monoalphabetic and polyalphabetic substitution ciphers. We will discuss this in detail. So let's first look at Pigpen Cipher. So the first substitution cipher would be changing the numbers in terms of drawings. So the Pigpen Cipher is that rather than replacing each letter with another letter, the letters are replaced by symbols like this. The cipher has an interesting history. Although its true origins are unknown, it has been used by many groups. Most notoriously, it was a cipher of choice for use by the Freemasons, a secret society in the 18th century. In fact, they use it so much that it is often referred to as the Freemason cipher. However, it was not exclusively used by them. with Union prisoners in Confederate camps, using it to communicate in the American Civil War. Okay, how do we encrypt the message? The encryption process is very straightforward, replacing each occurrence of a letter with a designated symbol. The symbols are assigned to the letters using the key shown here, where the letter shown is replaced by the part of the image in which it is located. So for example, I want to say, let's encrypt first. Suppose I want to encrypt Jack or math. Let's encrypt math. So math here, M would be like that because this is M, right? Okay, A is just this one. And then T, where is T? T is here. T is there, right? So it's like that. So T, oops. So I have T and then H. Where is H? H is there. Okay, there's H. So that's how you encrypt math. Okay, for the decryption, of course, the decryption process is just the reverse of the encryption process. Using the same key, you locate the image depicted in the cipher text and replace it with the letter given by that part of the grid. So let's try decrypting this message here. Okay, so for this one, where is that? That is T. That's T. And then this one, where is that? H, correct? So that's H. And then what else? This one here is I, and then S. This is I, right? This is, and then what do we have? This is there, A. This is, and then we know that this is S, E, and then where is that? C. I think this is secret message, I think. Yeah, this is a secret message. Okay. So next we have the Pigpen Cipher. So the Pigpen Cipher was used by the Freemasons in many aspects of their lives, and one of the most common still seen today is on gravestones. So here we have an image of a gravestone which clearly contains the use of Pigpen Cipher. So this is Thomas Brearley in Pigpen Cipher. Dancing Man Code. So what is the history of this Dancing Man Code? So in Sherlock Holmes' mystery, The Adventure of the Dancing Man by Sir Arthur Conan Doyle, Elsie Patrick received several disturbing messages that were written using figures of dancing men. So to decode the messages that she received, Sherman Holmes, the protagonist in that one, used two facts. The letter E is the most common letter in the English language, and it was likely that Elsie's name appeared in one of the messages. So there, Sherlock Holmes was able to determine that this is the code for the dancing men. Now, okay, so here are the messages in the dancing man story. So for example, here, what is the meaning of the flag? Okay, the meaning of the flag here is that after that letter, there is a space. For example, this one is A, that one. This one here is M. Okay. Is that M? Yeah, M. However, it is holding a flag, so that means there is a space there. Let me just write that down. And then this one, where is that? That is actually H. This one is E. Okay, let me just write that. Actually, when you decrypt this, here, and then that's a space there. Here, this is Abe Slaney. And then this one here, the criminal's message, for this one, this is actually, let's look at this. What is this? This is E. And then this one is L. It will actually be LC. Prepare to meet thy God. Okay? Now, let's look at monoalphabetic substitution, wherein the letters would really be replaced with another letter. So, for example, here, this is actually a shift cipher. So, I'm just using small letters to denote the plain text and capital letters to denote the cipher text. So here, A would be all the occurrences of A would be replaced by B. B would be replaced by C, and so on and so forth. So what we just did here is that we shifted the alphabet one position to the right. Okay? So for example, our plain text is a simple message. The ciphertext would be this one. A is replaced with B, S is replaced by T, I by the next letter after it, just that it. So if someone sees this and he doesn't have any idea that it was just a monoalphabetic substitution with one position shifted to the right, he would have no idea what this really means. Suppose we have this ciphertext. Let us determine the plain text. Okay, so N, so that means if we want to decrypt it, we go one letter back, right? So that would be M, B would be A, U would be T, math, correct? Okay, so this is what I said earlier, the shift cipher. Actually, this shift cipher is used by Julius Caesar. Okay, it was used by Julius Caesar for sending encrypted messages to his troops, as recorded by Suetonius. Of course, he doesn't want anyone to to know their battle plan. So if he had anything confidential to say, he wrote it in a cipher, that is by changing the order of the letters of the alphabet, that not a word would be made out. If anyone wishes to decipher this and get at their meaning, he must substitute the fourth letter of the alphabet, namely D for A, and so with the others. So meaning to say, this is just a shift key equals 3, meaning to say move 3 positions to the right. So that's why A would become D, B would become E, and so on. Alright? So the key, okay, so for actually if key is equal to 3, that's called Caesar cipher. But of course, key can be 4, 5, and so on. This is just the Caesar cipher with key equals 3. So this is our plain text alphabet, and this would be the ciphertext alphabet. So meaning to say K would go to N and so forth. Jump 3 places forward. And then of course, how do you decrypt it? you just jump backwards. So if you have O, jump backwards 3 times. So you would get L. So for example, you want to encipher the word secret. Now here what I did is this is the plain text, the black letters, and then the brown letters are your cipher text. So for secret, we will look at the what's this? The black letters. So that would be S would be encrypted as V, E would be encrypted as H, C would be F, R would be U, but E is H, and T is W. V, H, F, U, H, W. There you go. Of course, you do not need to have this table. You can just count with your fingers, right? So S, S, T, U, V, right? So that would give you V. And so on. Now, we want to decipher the word NLQJ. So again, even if you don't have this table, you can just go back. Of course, going back is more difficult, so it's better if you have this table. So we will now look at the brown letters because those are your ciphertext in order to get the plain text, which would be the black letters. So N would be K, and then L would be I. Oops. What did I say? N is K. Again. Here, where am I? N, 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 N. N would be K. So that's why N would be K. L. L in brown is I. Q in brown is N. And then J in brown is G. There you go. So therefore, the original message, the encrypted message is king. Okay, so let's now go to Atbash Cipher. So the Atbash Cipher simply reverses the plaintext alphabet to create the ciphertext alphabet. So as we can see over here, A would go to Z, B would go to Y, right? It's just the reverse. Okay, so that's why it is a very weak substitution cipher because it has no secret key behind it. So if anyone intercepts the message and then they were able to determine that it was used using Atbash Cipher, they can quickly get the message. However, one security measure that you can use is to use different plaintext alphabets. So for example, if you're just using this one, you can extend your alphabet, let's say, into A to Z and then include the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you can also put punctuation marks in it and then reverse it. At least it will add a bit more security to the cipher, although again, it's still not yet that secure. Okay, so suppose we want to encrypt the plain text at bash. So since we have here our table, it's better. So A would become Z, P would become G, B would become Y. Again, A is Z, S is H, and H at bash, H would become S. So this is now your cipher text. Let's decrypt this. If you have the cipher text XRKSVI, so X in the ciphertext, X is C in plain text, R is I, and then K is P, and so on. There you go. The plain text would be cipher, right? Let's look at that again. X in your ciphertext, where is your ciphertext? There, X becomes C. R in the ciphertext is I, and then K in the ciphertext, that's P, and so on and so forth. Okay, so this is what I was telling you about that you can put numbers to it and then punctuation marks to add a bit of more security in your Atbash cipher. So you have space and so on, this punctuation marks, your alphabet, and then your numbers, and then reverse it so that it would not be that obvious, because once the eavesdropper sees the Z, and then he figures out that Z it becomes A, then he will automatically know that it was encrypted using Atbash Cipher. Let's now go to Affine Cipher. Now take note that it is slightly different than the other examples here because the encryption process and the decryption process is substantially mathematical. The whole process relies on working modulo M, in this case modulo 26, and by performing this calculation, we encipher the text. Okay, so let's look at the formula here. So what happens is that for the encryption, okay, so first we take numbers A and B. Oops, actually this one should be 25. A and B should be, yan. A and B should be between 0 to 25 because we are working modulo 26. We just want the remainders when you divide a number by 26. Okay, first, we get two numbers A and B. And of course, A cannot just be anything. A should satisfy this property, meaning to say, it should not share any common factor with 26. So that's why these are just the possible values for A, right? All the odd numbers except 13. Of course, 13 is not there because 13 and 26, their GCD is equal to 2. Okay, so that's why 13 is not included there. Okay, so that's the first one. We have to get A and B, and then take note that these are all the possibilities of A. This is what you call your key, A and B. Once you know your A, you can get your C here because there's a C appearing here. Now, how do you get C? Here, it says that the product of A and C should be equal to 1 mod 26. So, for example, if you have A is 1, of course, C is equal to 1 because A times C is equal to 1. And mod 26, remember class that when you have mod, if it's already less than 26, it just remains as it. So 1 is just equal to 1. What modulo 26 means is that when you get a number greater than 26, you just get the remainder when you divide it by 26. Anyway, let's look at, for example, 3. When A is equal to 3, it says there that C is 9. Why? AC here is 27. Whoopsies, it's already greater than 27. It's already greater than 26. So, what is the remainder when you divide it by 26? The answer is 1. So, that's why it's equal to 1. It's congruent to 1 mod 26. You can also try the other numbers, okay? And you can verify that for all of them, the product of A and C is always equal to 1 modulo 26. So we follow this encryption here, and then we follow this decryption formula. So let's see how it really works. Okay, so let's see now how the Affine Cipher works. Now, remember here that for the Affine Cipher, what you need to do first is to translate your plain text alphabet with A starting with 0 and then Z ending with 25. Remember that, okay? So you have here, so these are the corresponding numbers. This is Affine Cipher, and then these are the corresponding numbers for each letter. Our key here is 5, 8. Okay? So all you have to do is, okay, this is the encryption formula, AX plus B, right? So obviously, if x equals 0, we have 5x plus 8 would be 8. So no problem about that. Remember, all of this happens modulo 26. Let's look at x equals 5. So we have 5 times 5 plus 8, you get 33. But remember, you want to make it mod, you want it to be mod 26. Okay? So what you need to do here, 33, when you divide it by 26, what would be the remainder? So it's closest to 26, right? So just 33 minus 26, you get 7. That's why you have 7 here and 7 here. Let's try x equals 8. So for x equals 8, we have 5 times 8 plus 8. So you get 48. There you go. How do you turn it modulo 26? Oops, I should write it 7. Mod 26. So get the remainder when you divide 48 by 26, right? So what are the multiples of 26? 26, 52, and so on, right? So the last multiple is 26. So you cannot be 52 because 52 is already greater than 48, right? So 48 minus 26, you get 22. So 22 mod 26. Is that clear? Okay, now, since you already have these numbers over here, you now look at the corresponding letters. 8 is actually the ninth letter, right? So that would be I. 7 is the eighth letter, which is H, and so on. Okay, so this is now the ciphertext. This is how you encrypt the plain text Affine Cipher. Okay, using Affine Cipher. Alright, so what we did in the earlier slide, in the previous slide, is encrypt. Okay, so let me just write here again my x for v. X equals 21. Our formula is 9x minus 5 mod 26. So we have 9, 21 minus 5. So 16 times 9, 144 mod 26. Let us divide 144 by 26. So the nearest is 5. 26. The nearest multiple of 26 is 26 times 5. So that's 130. So mod 26, the remainder is 14. How did I get 14? Remainder is 14. What would be, this would refer to the 15th letter. So V would become O. So actually, when you continue this process, the text there is mommy. Okay? Next, let's go to the generalization, mixed alphabet cipher. That's actually what we did, permuting or arranging the alphabets randomly. Now, take note that there are how many possibilities? There are 26 factorial possibilities for the mixed alphabet cipher. So one would think that it is secure, but then again, with a high-powered computer nowadays, it can be using brute force and then determining which one would make sense. Okay, with the ciphertext to plain text, which plain text message would make sense. Anybody with a high-powered computer can decrypt the message. Again, this is not secure. Anyway, so for the for this kind, since it it's just permutation of the letters, pero so that we can have a key, we have what we call a keyword. So what we do there is we write the plain text alphabet, and then we have a keyword, monoalphabetic. So what we do here is basically we just write down the letters of your keyword. But if you have repeated letters, let's say for example O, of course we cannot repeat it na, because otherwise if you repeat O here, you don't, when you go backwards, when you have O, you will not know whether it's B or D. Understand? So you don't repeat the repeated letters. So that's why you just have here monoalphabetic. Okay? And then once you finish your letters, you now continue with your alphabet. Okay. So since monoalphabetic, you now start again with A, but A is already there, so you cannot use it. B is already there. C is already there. So that's why you use D. And then E. E is already there. So you proceed with F, and then G, and then H is already here, so you no longer can use it. J, K, L is already here, and so on and so forth. Now take note also that for this, it is possible that the last few letters will just go to itself, no? So it's better that your keyword is a bit long with non-repeated letters. Even if your keyword is long but it has many repeated letters like Mississippi, in the end you will just have how many letters in Mississippi? M, I, S, and P. So you just have 4 letters here, and then for the rest, the letters will just go to itself. So it's better that what you have is a long keyword. Okay, keyword or key phrase. It's also possible, okay to use a key phrase. Okay, so for example, we want to let us encrypt um let's say what word? DLSU. Okay, what would that be? Using this, it would be A, L would go to C, S would go to R, and then U would go to U. Okay? So what about if we want to decrypt, um, let's say, um, decrypt A, E, M, F, F, L. What would that be? Maybe I should use small letters so that you know that it is a ciphertext. Ah, yeah, I should use big letters. Yes, 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 that's correct. Because this is ciphertext. So we will now look at our ciphertext. So this is our ciphertext A. It would go to D. And then E, ciphertext, would go to I. M, ciphertext, would go to A. And then F would go to N. I have 2 of those. It's actually Diane. Okay, so that's how you use this kind of cipher. Okay, polyalphabetic cipher, in this case, it is based on substitution. However, we use multiple substitution alphabets. So remember, in the first case, we had monoalphabetic ciphers. Remember, we have 2 kinds of substitution ciphers, monoalphabetic and polyalphabetic cipher. Now take note that for monoalphabetic, if you have monoalphabetic, the key difference is the same letter. If, for example, Z was encrypted as let's say L, all occurrences of Z would be encrypted with L. Okay? Whereas for polyalphabetic cipher, it's possible that the same letter C would be encrypted to different letters. Okay? So, what I have here on the right is a disk. Okay, this is the one used by Leon Battista Alberti in 1467. Now, Alberti would use this setting for a few letters of the message and then rotate the inner disk to a different string for the next few letters and so on. I will explain to you what this means, code E means. So as you can see here, if he's using the disk E here, this is code E. That means that in order to encrypt, he turns the inner disk to set the E here, okay? Find it in the outer ring and replace it with the inner ring. So meaning to say the outer ring would be the plain text and then the inner ring would be the cipher text. Okay, similarly, the decryption, this is the cipher text. You find the letters in the inner ring and then replace it with the letters in the outer ring. So maybe I should write that down. So the outer ring would be your plain text and then the inner ring would be your cipher text. Okay, so how does it work? So, okay, suppose we want to encrypt this, Leon Battista, the name of the inventor. Alright, now we start by referencing the starting position of the cipher disk, which in this case, okay, if you look at this one, okay, you have small letters and big letters. The small letters here represent the key for that particular for the next set of letters. So what this means, since you have a V here, it's like if you have a disk, okay, A would go to V. Is that clear? And then this is the plain text. This is like this is just a shift cipher, right? Shift with key equal to 1, okay? And then L, so as you can see here, there, L would go to G, that's right. E there would go to Z, there you go, and so on, right? Until O, let's look at O. O would go to J. I'm sorry. No. This is until 1, 2, 3, 4, 5, 6, 7. Which one? Until T only. T goes to O. So this is until Leon Bat. Correct, right? Leon Bat. So, after that, it turned to small letter G. So that means you now turn your disk, if you have your disk, or this one, if you have this. So A would now go to, look at that, A would now go to G. So you are now using this one. So we finished with, let me just highlight that. So for the first part, for this one, we had Leon Bat. Okay? And then next, this one, I think something is missing here. I think this one is Alberti. Something is missing, Alberti. Okay, so anyway, so let's look at G. Okay, so under this, let's look at T. T would go to Z, right? So this is your, and then I, for this I here, would go to O. There you go. Okay, and then S would go to Y. There you go, and so on. Now here, for the last one, that's M. Okay, how many letters is this? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. I think that's until A. Yeah, until A. That's, am I right? G. Leon, but anyway. And then M. So here, for the last A goes to M. And then what is that? Yeah, this is, where am I? L. Okay? And then B goes to Alberti, goes to N. So that's why you have N here. E for Alberti. E goes to Q. Okay? R goes to D. There you go. T goes to F. And I goes to U. Is that clear? So remember, class, that the small letters here says that you have to change your alphabet already. Okay? Okay, so another example of a polyalphabetic cipher was invented by Johannes Trithemius in the 15th century. So what he did was he keeps on switching the code, meaning to say, let me just show you how it works. So for example, I want to encrypt math. Okay, so for the first letter, I will now look at my first column. Okay? So remember, the letters inside, that will be your ciphertext. Okay, so the letters inside, so inside that will be your ciphertext. And then outside here, oops. Okay, this number is outside, that would be your plain text. So for the first column, I will look at math. So M. Okay, so of course, under this first column, the ciphertext would be M. Okay, next, for the second letter, I have A. So since this is the second letter, I will now look at my second column. Okay, and then my plain text is A, so it will go to B. So A, there you go, that's B. And then T, that's the third letter. So I will look at my third column here. Where is T here? There. There you go. So that would be V. And lastly, H. H, that's the fourth letter. So I will look at the fourth column. So for D, and then where is H? There you go. H would go to K. Understand? So this is now K. So that's how you decrypt math. Now, similarly, for the opposite, for the decryption, you just look at your letters here inside. You just look at your letters here inside and find the corresponding letters outside, because remember that these are your plain text. Okay? So, anyway, let's now go to Vigenere. I don't know how to pronounce it. Okay, let's just say that's Vigenere. The Vigenere encryption was the creation of this French diplomat. He viewed the cipher as a substitution cipher where a different alphabet was used for the next letters of the message, with the alphabets repeating periodically. However, we are now looking at some key. So how does it work? Okay, so how does encryption work here? So first, you need to get a key stream or a keyword or key phrase. You then repeat this keyword over and over until it is the same length as your plain text. And that is what you call your key stream. So for example here, my keyword is Batista. But I still need more letters here, right? So I will just repeat Batista until I finish my plain text. This is what you now call your key stream. Now, how do we encrypt it? Okay, first, let's look at the plain text and the key stream and the letters here. Remember here, just that the letters inside would be your ciphertext, and the letters here would be your plain text. So, you have here A. You now look at the column B, okay? You now look at A, since we want to encrypt A, B, A under column B would be represented as B. Okay? So that would be B. Next, we want to encrypt S, but we now look it up under column A. Alright, so where is S here? S would go to S. Next, let's go to I, but we will look at I under column T. Under column T, and then where is I? So, the intersection of those under column T, so that's B, right? Am I right? I, T. Yes, correct. That's B also. And then M under column T. So M under column T, where is T there? And then M, duling na ako. No, that's N. Yeah, that's F. Alright? One last. Let's look at P under column I. So P under column I is X. Okay? So if you continue that process, BSBFX, right? And so on. So yes, we are on the right track. You would be able to get this cipher text. Okay? How do we now decrypt it? So similarly, it's just the opposite. So remember that these letters here are your ciphertext, and this one, these are your plain text. So for example, the key stream here is Giovanni. Actually, the keyword is Giovanni. So just Jovan, sorry, Jovan. Okay? Now, Jovan. Okay. Now, let's look at Z, but we will look it up under column G. So this is column G, but this is our ciphertext. So we look for it inside, letter Z inside, no? So therefore, the corresponding plain text is T. Okay? T. Let's look at one more. Under the column I, we will look for the ciphertext P. Under column I, where is P? There you go. So that's H. Okay? H. Let's make it small so that we know that it is plain text. Next, we'll have S. We'll look for S under column O. Under column O, we'll look for S. There. That's letter E. Understand? So when you continue that process, what will it be? That would be the unbreakable cipher. So before, they thought that this cipher is unbreakable. Actually, it is not. Of course, with the use of computers you can break this kind of cipher. Now, you can also have Vigenere Cipher without you making use of that big table over there using numbers. So for example, this is what I want to encrypt, save, okay? So again, I'm starting with my first letter A as when you write it as a number as 0. So again, we will be working modulo 26 here. So save, this is what we want to encrypt. S is 18, A is 0, V is 21, and E is 24. Now, blade is my keyword, blade. So I will only end up until D. Now, as numbers, that's it, 1, 11, 0, 3. So what you just need to do using Vigenere Cipher, you just add. Okay? So 18 plus 1, 19. Okay? 0 plus 11 is 11. 21 plus 0 is 21. 4 plus 3 is 7. And then you now get the corresponding letter. So that would be this one. Again, if you get a number which is greater than 26 here, you just perform modulo 26. So for example, if you get 28, what would be that number mod 26? The answer is 2. Understand? So now, upon our discussion, what is now more difficult to decrypt? Monoalphabetic or polyalphabetic cryptosystem? Of course, the answer would be polyalphabetic cryptosystem. But again, this kind, even if it's difficult to crack, you can still crack it with the use of computer. So in our next video lesson, we will talk about a more secure way of encrypting our messages. And that's what we actually use nowadays. Okay?